Lawrence, who will tell us about the Hubble diagram and quasars, and please.
Thank you very much.
The floor is yours.
So thanks for coming. Thanks, Bojena, for inviting me. And I'm presenting today a very new work that we started a few months ago, but the root of this work are, back in, they are 20 years old. So it's a new way to do cosmological measurements based on quasar properties, which in principle have been known for many, many years, but as I will show you, only recently reached the precision required to be useful to do cosmological measurements. So I will just briefly introduce the topic of cosmological measurements, giving for granted the standard cosmological model, and then I will show you how we can use quasars to learn something about this cosmological model. And I don't know, I think the audience has different expertise in astronomy and cosmology, so please ask me anything if you need clarifications. And so from the very beginning, the so-called Hubble diagram has been, since the beginning, the main tool to try to understand the general properties of the expanding universe. Actually, it is the diagram which first showed the expansion of the universe, and even today it is still the main, or one of the main tools used to constrain the parameters of the cosmological models, because there is one which is called the standard one, but maybe the most interesting part in research is trying to find deviations from the more standard picture. And so this is a velocity-distance relation among galaxies, and so there is a velocity which is now interpreted as simply the expansion rate of the universe, and this is distance. And here distances were calculated based on some estimate on the intrinsic galactic luminosity. And it's nice to see that, this is maybe one of the most important discoveries in astronomy, but the constant of this relation was wrong by an order of magnitude. The Hubble constant, which is called Hubble constant from this diagram, was estimated by Hubble to be about more than 500 in kilometers per second per megaparsec, which is about an order of magnitude higher than we measure today, but nevertheless the principle was set. So the main point from 1929.
What was the reason for this discrepancy?
The reason basically is that, and I exactly coming to this point, is that while measurements of the velocities, or the redshift, were already precise enough at that time, and are for sure very precise today, at least for spectroscopic samples, the distance is the problem. The problem is the distance, and here the intrinsic, because the distance is estimated as a ratio between observed fluxes and intrinsic luminosities. And which is the intrinsic luminosity? So from this diagram until today, one of the main points of observational cosmologists is to find standard candles. So sources for which we can give a good estimate of the intrinsic luminosity, and so from that estimate of the intrinsic luminosity and from the observed flux derive a good estimate, a good measurement of the distance. And then from the distance redshift diagram, which is the Hubble diagram, then we can infer information about cosmology. And so let me, yeah, that was the value. Now it is between 65 and 70, these units. So let's jump to 2004, and then I will show you an even more recent diagram. This is the same, basically the same thing, made with the same units, Okay, so it's an old-fashioned plot, but it's been made just to compare with the previous one. And first of all, the scale. The original Hubble diagram stays in this very small red square here in the corner. So you see the huge improvement, but the most important thing here is not only the improvement in the distance redshift scale, but the precision of the distance measurements, because this Hubble diagram is now based on type 1a supernovae, which are believed to be close to standard candles, and I will say something more about that in a few minutes. And so that was just to compare with the previous one. Let me show you a more modern version of the same. Okay, this is so the colors are not perfect. My apologies for that. And anyway, this is the most updated Hubble diagram in the modern units. So we have redshift here and distance modulus here. So the distance modulus is basically the, as I say, the ratio between observed flux and intrinsic luminosity. Okay? And this is the redshift. And so here, at least for astronomers, it's a more convenient unit than the one before. And you see that supernovae, each point here is a measured supernova. They are about 500. And I took this sample from this group, the Supernova Cosmology Project, which is one of the two groups which first used this diagram with far less points to find that the universe is accelerated at the end of the 90s, and they got the Nobel Prize in 2011 for this. So basically, this is the same diagram which got the Nobel Prize, but there were only 40 supernovae at that time, and in these almost 20 years, they improved a lot. And they improved not only in the number of sources, but also in the redshift extension. Here, today, the farthest measured supernovae are as far as redshift 1.4, which in terms of time age of the universe is more than half. Okay, so we can see supernovae in, let's say, the second half closer to us of the universe, and even more. Okay, so I think with redshift 1.4 means an age from the Big Bang of probably something like 5 billion years, and so it's about 9 billion years from now. So it's more than half. And of course, it's very difficult to improve in the sense of going to higher redshifts, and that's what they are trying to do. So using this diagram, it is possible. Oh, the intrinsic scatter here is very low. The intrinsic scatter basically is due to the residual uncertainties and systematic uncertainties on the estimate of the intrinsic luminosity of these objects. I'll show you more soon. And so we can use this to fit to these points the distance redshift relation predicted by the standard cosmological model or any cosmological models, and try to get the parameters of that model as through a best fit procedure, and in particular using the standard lambda CDM model, so assuming the parameter omega matter is a total of matter, so including dark matter and baryonic matter, and omega lambda, which means that we are assuming a cosmological constant, like in the original Einstein equations, without evolution or changes in the dark energy component. Then we can improve from that, but just from as a starting point. And we can do that, but it is very important, and I think this is a crucial point even to put in the right place the work on quasars that I will show you in a few minutes, that this very fundamental piece of observational cosmology is based, as I said, on supernovae, which are standardizable candles. I mean, they are not standard candles in themselves. It's not true that every supernova has the same intrinsic luminosity. I mean, it would be too simple. In reality, what happens is that the scatter in luminosity among supernovae is too high to do a good cosmological measurement with supernovae. And the breakthrough came in the 90s, where they realized that there was a tight correlation between the luminosity at the peak of the supernovae and basically the rate of decrease of luminosity. Why? Because observing the decrease in luminosity of this supernovae, one can correct the observed luminosity, finding a really intrinsic luminosity. So we make something which is not a standard candle, we make it a standard candle through this observation. So the observation of the light curves of supernovae can help to reduce the scatter, and the 10% scatter that I showed you in the previous slide is thanks to this correction. Without this correction, there will be no cosmology done with supernovae. This correlation, which is called the Phillips relation, because from the author of the paper with this discovery, has been basically tested only at redshift below 0.1. So everything we know about cosmology based on supernova is based on the assumption that this kind of relation does not evolve with redshift. So we measure, we are safe about this relation in the local universe. We assume that it is correct at all distances and all ages of the universe, and then we can build the diagram that I showed you before, and we do all the cosmological,
And this correlation is only observational, or it is based on some...
No, there is no theory, on my knowledge, that explains convincingly this correlation. It's observationally. Because basically when we go to very low redshift, the cosmology becomes linear, the Hubble diagram becomes linear. So we do not need to know all the parameters of the model, and we see that this correlation holds.
Why is it difficult to find these curves for higher Z?
Oh, well, basically, it wouldn't be difficult to do this correction. It's almost impossible to find supernovae, because supernovae are transient sources, and we need a very high area surveys.
And because it's only 20 or 40 days that you have to...
Yes, but in order to find this, we have to find the supernova close to the peak, and so, you know, we have to sample huge regions of the sky to find one. They are trying, and every year they find a supernova which sets the new record, but it's a difficult task. Anyway, people working on this field are all working to improve this and finding.
Does it suggest that each supernova explosion is in some sense universal? The same physical mechanism stands behind the explosion? Because there is some universality, you show us, yes?
Yes.
And it doesn't depend on anything, on the mass of the...
Yes, because basically supernovae...
Only the
It
scale.
does depend on the mass.
Yes, but there is some
by a small factor.
Yeah,
The reason why there is such a small scatter, even before the correction, is that supernovae 1A are believed to be created when a white dwarf explodes, but it's a white dwarf which is accreting from a companion star, and it explodes at a given critical mass.
Okay.
So at the moment of explosion, they are all
almost the same.
Almost the same, but not enough to do cosmology without this, this relation. So this is just one of the most recent plots showing the measurements of these two parameters with the contours and the errors, and the supernovae are the green ones. And you see that there are several other methods. I'm not going through them now, but there is the CMB, the cosmic microwave background radiation, which give very tight constraints basically on omega lambda plus omega m. So it's almost the line in this plot. And then we have baryonic acoustic oscillations, and we have studies of galaxy clusters, relaxed galaxy clusters. There are other methods which all give a contour, a contour plot, and so a possible region for these two parameters. So why am I showing this? To say that the people working on cosmology in any of these fields, they all say that you see that, for example, within the standard model, these two parameters are very well measured now, because the intersection among all these measurements is very small. So we have an omega m 0.3, omega lambda 0.7 fiducial values, and let's say there is no need to be more precise. We are precise enough. So what is the role of new cosmological studies starting from this? First of all, as I showed you, there is a need for confirmation of what we are estimating, because in many cases, in all these methods are relying on strong assumptions, like the one that I showed you on the Phillips relation. Okay, so they are assuming that something works regarding the spectrum of primordial fluctuation from the CMB, and so on and so forth. And so they all agree that before saying that we know the answer about cosmological models, we really need more independent ways to estimate these parameters. Secondly, maybe the most important part physically is to check for deviation from the standard model, and in particular about the nature of the dark energy. Is it a cosmological constant, so is it a property of space-time, or, oops, that shouldn't happen, sorry. Or is it or is there an evolving equation of state for dark energy? Okay, this is something completely open, and we need more precise observation for that. So, based on this framework, let me introduce what we can do with quasars, and then it will be clear why I believe it's a good and important step forward in this field. Okay, quasars are very luminous objects, and they are easily observed, well, not very easy, but they are observed up to very high redshifts. So they will be perfect standard candles. They are easy to observe, and we can observe them also in the early universe. However, until now, all the attempts to make them standard candles failed, because there is no obvious spectral indicator of the intrinsic luminosity, and they are also highly variable. And so there were several attempts based on light curves, based on seeing how quick one part of the quasar responds to a variability of another part, which is reverberation mapping, and so on. And one of these is the luminosity dependence of the UV to X-ray flux ratio. So, and I'll focus on this. So all these were being largely dismissed because the uncertainty was too high. And let me go on the last one. So what do we need? What do we need in practice to make quasars standard candles? They are not standard candles. They span 7 orders of magnitude of intrinsic luminosity. So we start with something which is not at all a standard candle. So when I say we have to make them standard candles, I mean that we have to find a way to estimate their luminosity. There is no way to select a subpopulation of quasars with the same intrinsic luminosity, like with supernovae. Forget it. Okay. So
some people try.
Yes, but it is. Yes, exactly. But I have never seen measurements of the cosmological parameter with that way. I mean, it's a long way. Maybe at some point the data will be good enough to succeed in that. But for now, we are not at that point. So the way to try to make them standard candles is to find something in their emission. Okay, quasars have emission all over the electromagnetic spectrum, which is an indicator of intrinsic luminosity. Okay. And we know that there is something like that when we measure the ratio between X-ray luminosity of quasars and their UV luminosity. So it's like the Phillips relationship. We do not know why. There is no physical model explaining why, but observationally, we see that this ratio, which is defined, I can show you, basically it is defined as the slope of a power law connecting the UV emission with the X-ray emission. This is technically how it is defined for more expert astronomers, but the point is that whatever the definition, there is a dependence of this ratio with luminosity. So more luminous quasars have lower ratios between X-ray and UV emission. So it's still true that more luminous quasars are also more luminous in X-rays, but it doesn't go linearly. So the ratio between X-rays and UV luminosity can be 5–10% in low luminosity quasars and can be lower than 1% in very high luminosity quasars. So in principle, I can use that ratio, which is an observational ratio, and since it's a luminosity ratio, it's the same as saying it's a flux ratio. Any cosmological distance dependence will cancel out doing the ratio. I could use this ratio to infer.
But to use this ratio, you must know somehow the distance.
That's the point. So in these plots, these plots are all plots which have been made by people who weren't interested in cosmology. So they were assuming a distance from the redshift of these objects and assuming the cosmological model measured by somebody else. Okay? And they were using these plots just to show, look, there is this physical relation in quasars. So they were using the results from cosmology to estimate the distance and to plot something which is a physical relation. So now we want to do the other way. So I agree, we cannot use luminosity. I mean, we can, in these plots, I'm sorry for the quality of the plots, but anyway, here we have luminosity. And of course, if I plot something with luminosity, I cannot do cosmology with that, because how do I know luminosity? It would be, okay.
One more issue. May I have a look at the previous slide? So of course, those results should be independent. How you choose those energy, like 2 kV or 2500, they are more or less independent of the choice of those two energies, yes?
More or less.
But
we made
those
some
numbers are taken arbitrarily, or?
well, basically they have been chosen historically because they are relatively easy to observe, at least for the initial quasar samples. Then we made recently some check, and it doesn't change much depending on which frequency we choose. So this is the same, but let's say instead of plotting a ratio versus the luminosity, we directly plot the X-ray luminosity versus the UV luminosity. So here we are using cosmology. We cannot use this to infer anything cosmological, because we are using the cosmology to measure the luminosity. But this is just to show that you know, there is this tight correlation, and it is not linear. The slope of this correlation is not 1, it's 0.6. Okay. So the consequence is that, I mean, this was known for more than 30 years. The problem is the precision. Because the point is that if we start from a linear correlation between the X-ray and the UV luminosity with a slope which is not 1, we have just to write the luminosity as a function of the observed flux and the distance, and in this equation the distance doesn't cancel out because this alpha is not 1. So if I write, I mean that's very easy algebra, if I write this equation here and using the definition of luminosity as observed flux times distance squared, I just get an equation which has observed quantities, because this is flux, so this is the observed quantities, and the term which contains the distance. And this distance is something which depends on the cosmological model that I use in the standard lambda CDM model. This is the distance, and so we can use this equation to fit the parameters that we are interested in.
I have one problem. Under the logarithm, you have luminosity.
Huh?
Under the logarithm, you have the luminosity.
Exactly.
And the luminosity is measured in some units.
Exactly.
And this unit could be slightly modified when you go from one spectral domain to a different spectral domain.
Exactly.
This way you could easily absorb beta by changing the
Beta. Yes.
absorb. You can bring it under the logarithm.
You mean this one? Yes, I mean the problem is that since we don't have any physical model for this relation, this beta technically is left as a free parameter in the fields. Because
So the luminosity is measured in the same units, even though it refers to different spectral
yes,
units.
absolutely, absolutely. And actually this is the starting point, but we never measure luminosities, because what we do in practice is to use this relation and measure, here we measure flux in X-ray, flux in UV, and redshift of the object. Redshift is inside the definition of distance. Then we fit this correlation having as free parameters the alpha and beta parameters of the correlation, because unfortunately they are unknown. We need a physical model which predict them, but for now we don't have. So we have these two free parameters plus the free parameters of the model. So in this case, assuming a lambda CDM model, we have omega n and omega lambda. Oh, unfortunately, this parameter beta is degenerate with the Hubble constant. If you do some calculation, it's easy to see it. So we cannot, with this method, measure the Hubble constant, because the Hubble constant is degenerate with this parameter of the correlation. So unless we find a model which gives us an estimate of this beta independent of the observations, we cannot measure H0. And so this everything, yeah.
I have one simple question. How does the spectral distribution look for such an object?
Yeah,
Can you draw?
I can show you.
Probably it is not a Planck distribution.
No, not at all. So if I show you nu f nu for a quasar, and let's say I start from, let's say here I have infrared, okay, so huge range of frequencies. I have optica, UV, and X-rays, okay. The typical spectral energy distribution is something like this. Okay. So there is a peak which is around, it is in the UV, okay, it is around the hydrogen edge, okay, so in terms of energies at about 13 eV if you use it, or you know, it's hydrogen edge. So the 2 kV that we use are around here, and the 2500 and some are around here. Okay, so we use this, and basically our models of quasar emission say is that basically this is the primary emission of a quasar, which is due to an accretion disk around the black hole. So this is the superposition of black bodies, basically. So because each ring of the disk is a black body, basically. And the X-rays are secondary emission, which is due to inverse Compton scattering on the seed photons from the disk by a cloud of hot electrons surrounding the black hole. This is the general scheme. And the reason why we use this point and not this one, for example, is that, well, it's easier to observe, but also starting from around here, we have problem with absorption by the intergalactic medium. So it would be very hard to measure the intrinsic luminosity, the intrinsic flux close to the peak, because we should correct for absorption for far objects or absorption by the intergalactic medium, and that would, it's possible, but it will introduce a large error. And what we need is instead precise measurements. So that's more or less.
And now you claim that there is some relation, huge correlation between these 2 points in intensity. You claim that from these observations that there is some correlations, and
Yes.
we
Yeah,
don't
because
know
it,
why.
it works
So what
like the
happens
ratio
is
of those
that-
2 components, right?
Well, if you take a more luminous quasar, something like that,
Okay.
okay, so this is the difference at the peak, the difference in X-rays is smaller. So probably the density is something like this. Okay. That's how it works. Okay. So everything I've said, I have described so far, could have said 20 years ago. Okay. So there is nothing new in this, and indeed it doesn't. I don't even know if somebody tried to use this correlation for cosmological purposes. Maybe somebody did, but never published because it doesn't work. You can try with all the published samples, even the most recent ones that I've shown you in here. These were the 3 samples. You see 300 quasar, 500, and 300. These are the best samples published so far, and this is the combination of these 3 samples, so more than 1,000 objects. And with this dispersion, it doesn't work. What do I mean it doesn't work? It is not technically. Technically it works. But when you do the contour plots of omega m and omega lambda, you find simply that they cover all the parameter space. So they are unconstrained. The precision is not enough to get meaningful measurements. Okay. The reason is that the dispersion of this correlation is too high. Why? Well, it may be intrinsically high. No? So this, that correlation that I sketched there may be intrinsically not so tight, but there are also a lot of observational problems. And in particular, galaxy contamination at low luminosities, which makes difficult to estimate the UV flux due to quasars and to separate it to the component due to the galaxy. There may be intrinsic quasar reddening. So a little dust along the line of sight can alter the measurement a lot. And so we may have a huge uncertainty in the huge, even an order of magnitude error in the measurement on this luminosity. Then X-rays, especially for the faint objects, are very hard to measure because of high background problems. I do not go into technicalities of X-ray observations, but believe me that in low signal to noise data, first of all, we have large statistical errors, but they are hidden systematics very often, which make the observation, the measurement not reliable. And then, as I said, it can be that there are intrinsic differences. Okay.
Yeah, because
So-
here you have a combination of the black hole mass and Eddington ratio.
Exactly.
And that's the source of the problem, right?
Exactly. At least for the intrinsic part. So, is it possible to improve these points? Well, it is possible if we try to select objects which have high signal-to-noise observations, and that they are intrinsically not affected by extinction or galaxy contamination. And in doing so, probably, we are also selecting a subpopulation of homogeneous SCDs, which also reduces the intrinsic scattering. Okay? So one can say, okay, let's start from the sample that I have, and let's really try to keep only the objects for which I am sure that the observations are reliable. We can try, and again, it doesn't work. Why? Because we end up with 100 objects from more than 1,000, and they may be reliable, but they are not enough to constrain these cosmological parameters. Again, the breakthrough is with much larger samples. And our contribution has been to increase the sample of quasars with available UV and X-ray measurements by a factor of about 5, because we have now more than 5,000 objects. And this is basically obtained cross-correlating large UV surveys, optical surveys of quasars with X-ray serendipitous observations. So we have catalogs now of hundred thousands of quasars found optically with the measurement of the UV luminosity. And then we take this huge list and we check how many of them have been observed by chance by an X-ray observatory. And we find that there are more than 4,000. So adding to the previous 1,000, we get these numbers. Then we can apply these very strong quality filters, and I stress that they are quality in the filters in the sense that I'm not doing any selection which is related to cosmology. I'm doing a selection which is related on observational aspects of data quality based on on the observational conditions. So it's not a physical selection. Okay, it's an observational selection, and we end up with 900 quasars. So the same, more or less the same size as before, but this time with good measurements. And let me show you, this is the distribution of the observation in observed flux, observed in X-rays and UV, and this is observed UV flux and redshift. So these are the remaining 900 quasars, and you see this was the initial sample of 5,000 objects, and you see here that how the spread is bigger. So basically we clean this sample for most of the wrong observations. And when we do this, we can start trying to use it for cosmology. And this is the last important technical step, because once we have this clean sample and we want to try to use it for cosmology, using it for cosmology means that we are using that linear relation that I have shown you before, and we assume that it's valid. And we use that as a framework to fit the cosmological parameters. Like people on the supernova project, we assume that the physics relation is valid for all over the universe. But here we can do better, because we can split the sample in narrow redshift bins, so in narrow distance bins, okay, and check if the relation holds at all redshifts. So we do not have to assume that it holds at all redshifts. We can check, okay? And we split our sample in 20 small intervals and check within small redshift intervals. These are just an example, and this is the results of fitting the same linear correlation. And this is the slope of the correlation. You can see that it's perfectly consistent with being constant. So we can assume that it is constant at all redshift and use it to fit the cosmological parameters. Okay, yeah, this is a more longer list of, so basically you cannot read the numbers here, but this is the same correlation fitted to subsamples at different redshifts. Okay, and we always get the same value of the slope. So this is a strong starting point, because we can see that the highest redshift are redshift higher than 5. So we know that this correlation holds up to redshift 5. Okay, results. So now we have all the ingredients, and we can try to use this correlation to build our own Hubble diagram. And you see this is the same as the third slide that I showed you. What happens if I put our results on this plot, and this is what happens. So the gray points are the individual sources, and so as you can see, they are much more scattered than supernovae. Okay, the residual scattering is much higher, so it's much better having one more supernova to add in this diagram than one more quasar. But quasars are many more. And I can tell you that this work has been done quickly, but these 900 quasars can be improved a lot, easily. Okay, and you know, there is a lot there are many samples in the literature that we didn't consider, and there are forthcoming surveys, especially in X-rays, which can increase the number quite a lot. So I think this is just the beginning. Anyway, the red points are the averages of the gray points in redshift P. So you see that there is a perfect match.
Can you go further to the right with quasars?
Thanks for the question, because this is very nice because it shows that there is a perfect match. So I would say that this is one of the requirements of the cosmologists. Find something which is independent and can check the previous method. But this is the first time where we have a completely different method which can measure the same thing. I mean, it's impossible to make an Hubble diagram with the other methods, because the other methods measure the cosmological parameters not through a Hubble diagram, but through other properties, the fluctuation of the primordial background and so on. So this is you know, we can do a complete check, cross-check. So I think that the two methods validate each other. But, and thanks for the question, you can also see that if I just stop here, the main contribution is a validation of the supernova method, because it will be very hard, even increasing the sample, to do better than supernovae. Because supernovae are already 500 and they have very little dispersion. So my aim is not to improve this diagram, but my aim is to go at higher redshift. Here we go up to 1.4, and this is the same diagram. And you see, what I showed you in the previous slide is just this part here. Because now the redshift is no longer up to 1.4, but up to 6. So this part here, with the fit, with the standard model I will show you in a minute, this is the first time we can probe this part of the universe. So all our measurement and test of the cosmological model was based so far, were based so far either on low redshift sources or on very high redshift information, because the CMB fluctuations are from a redshift or higher than 1,000, a few 100,000 years after the Big Bang. So it's a different physics, okay? But this samples the evolution of the universe, let's say, in the first 5 billion years, which was completely missing. And you see that the data quality is not great. There is a lot of improvement needed here. So it's just the beginning, and we also plan to ask for new observations in this range, but it can work. This is just a few tens quasars found in the literature. It can be improved a lot. So let me show you our results. This is basically the yellow and red contours are our estimates from for omega n and omega lambda, and these contours are from supernovae, and the blue and green contours, these are 1 and 2 sigma contours, are the intersection. So as I said, the plot that I've shown you before is more precise than this, but the point is not improving the precision of the measurement. The main aim is to test this model in the other half of the universe, which was still missing, okay? And so here I show you how it could be improved in the near future, thanks to wider X-ray surveys, which we provide about 50,000 new observations of quasars, okay? And this is already scheduled. This is with the satellite which should be launched next year. So it's not you know, a dream. It's something which the numbers have been taken by the technical book of this satellite, and you see that we could improve the measurement quite a lot. So we could be able to measure the cosmological parameters with the same precision as possible now, but only with the Hubble diagram. So just looking at the expansion of the universe, we can completely constrain the cosmological model, independently from our analysis of the primordial fluctuations, which of course are very important, but they are also physically dependent. So I think that this is physically important.
Sorry, excuse me. Is there any simple explanation why these two methods are in some sense perpendicular on this plot?
Yes, there is. I mean, it's not that simple, but there is one. And so basically, it can be shown, playing with the equations, that basically, since these are both Hubble diagrams, so they are homogeneous measurement, it depends on the average redshift. So the supernovae sample is all biased towards low redshifts. So not only it's only up to redshift 1.4, but the majority of the 500 supernovae are at low redshift. So the higher, if you do simulations with the sample with the same properties, and you just increase the average redshift, you see that this tilts this way. Okay. So if I replace my quasar sample with another quasar sample with the same redshift distribution as the supernovae, I will find the same contour with the same inclination. So since they are homogeneous, the fact that the intersection is almost spherical is the let's say is an indication that using all the redshift range, at the end you will find you know, more or less the same precision on both parameters. If you study the equation, you see that the optimal redshift distribution of the sample will be uniform in logarithm of redshift. So it's okay that we have more objects at low redshift than at high redshift, but now the actual sample is even too biased to low redshift for supernova. So that's why we did. And let me finish with possible extensions of the standard model. No? So new cosmology, the equation of dark energy, and this is just an example to show the possible application of this method, because there are many different ways to study modified gravity and so on. Here is a sample. Is an example showing the same omega m parameter, but instead of assuming a cosmological constant, we assume a dark energy with an equation of state, which is constant with redshift. And this, just to give a connection, the previous model is equivalent to assuming that it is -1 in the cosmological model. So this is just adding one more free parameter, assuming that the cosmological constant is not a property of space, but is some form of dark energy which has its own equation of state. And this is, within this model, the measurement that we could do with quasars and supernovae. And this is my last slide. This is the comparison of our future work with the increased quasar sample compared with the best that can be done today. So as you see, they are comparable. Ours is even better, and it will be even better once we use not only supernovae but also these other cosmological methods. So there is I mean, I think that these are the conclusions, but basically the main conclusion is that this method can open a new branch of cosmology, both because for the first time it tests the cosmological model in a range of age of the universe which was totally unexplored. Second, because maybe not today, but in the near future, it can be precise enough to improve our constraints on the parameters of the cosmological model, and in particular on the cosmological models, including an evolution of the dark energy properties. And I'll stop here. Thank you for your attention.
So all you need now is more measurements in X-ray and
Yes.
Because that observation, I think, is very interesting that you can use the average. So
Exactly.
you don't have to worry about the details of this quasar.
Exactly.
And the average,
Yes.
at least for low Z, was perfect.
Yes, and actually, it's going into details since you are asking. What happened is that to make this diagram here, we relaxed the quality requirements at high redshift because otherwise today we would be left with 10 objects. So, and it's interesting to see that until redshift 3, where we apply strict quality criteria, it follows perfectly. Now it starts to deviating, and indeed here we need more observations.
So the statistics is better.
Yeah. And regarding the intrinsic scatter, we try to investigate it with a subsample of really good quality, simultaneous observations and so on. And we haven't finished yet, but our conclusion is probably that 2/3, so more than half of this dispersion is intrinsic. So the way to go is not trying to do more precise measurements, but to increase the amount of exactly.
One question, yes.
I didn't understand the conclusion. For this bright future, you need more observation or more data analysis?
More observations. We also need some more data analysis because we haven't completed the job that can be done with the available observations. But that can be an improvement of a factor of 2. So it will be a good paper, a good new paper, incremental measurement, but not a breakthrough. To have the breakthrough, I think there are 2 ways. Waiting for these wide area surveys, and also doing specific observations in this redshift range. Because here, even a few tens new observations, but well selected, can make a big difference. Especially from the physical point of view. Because I don't expect that with 50 more objects here, I will do incredibly better measurements. But physically, I will have a much better test of the cosmological model in these redshift ranges. As I said, here the point is not to have a better measurement of omega m, because omega m today is estimated to be 0.27 plus or minus 0.001. 0.01. So, yes, it's interesting to do even better, but I don't think it's terribly important. The important thing is the physics here, because we are assuming that we have a global model for the universe, but it's tested only in relatively small parts. So that's, for me at least, is the most relevant point.
Thank you very much.
Thank you.